So I think we can start. This is the first event in the Millennium series, which is organized by the DMV, whose aim is to celebrate the Millennium Problems, which were formulated in 2000, and for each of which a prize of $1 million was set up, which maybe seems a lot, but if you work on these things and have to do with third-party funding, it's really a very small sum for such difficult problems. Anyhow, so in Münster we will be doing the Birch-Swinnerton-Dyer conjecture, and there will be two lectures, one by Guido today. Guido Kings, Professor Dr. Kings, who's from the University of Regensburg, and he will speak to mathematicians about the Birch-Swinnerton-Dyer conjecture. And in 2 weeks, Professor Sarah Zerbes from the ETH in Zurich will give a public lecture on the same topic. Now, our speaker, Guido, is very well known to us because he studied, well, he did his diploma in Bonn with Günther Harder, and then he joined my group and he did his PhD and later his habilitation here in Münster. And after writing his habilitation, in around 2000, he immediately got an offer to a chair at the University of Regensburg, where he has been working ever since, interrupted by stays at universities like Oxford or Cambridge or Paris, things one does. Now, Guido's work has been in arithmetic algebraic geometry. Especially, he has made especially deep contributions to the theory of special values of L functions, and especially on the Bloch-Kato conjectures, on Iwasawa theory. Even higher analytic torsion appears in his work. He has recently made a breakthrough with his student Johannes Spranger on the Deligne conjecture for critical values of Hecke L series in the general case. And he has several other important papers, also, for example, with Beilinson, who was one of the founders of this theory of special values, and Levine on the polylogs, and on the construction of p-adic L functions with Sarah Zerbes and David Löffler. And if one looks at these papers and works and listens to him, I'm always awestruck by the deepness of the theorems and the deepness of the insights, and how conceptual these insights are. So the results are great, and the methods are also great. So I always feel like my eyes are opened. So this I can say. And so we have now this brilliant expert who will explain to a general mathematical audience all about the Birch-Swinnerton-Dyer conjecture. I should also welcome all the listeners on the live stream, and not only the audience, which I also forgot to welcome. Okay, thank you.
So thank you very much, Christopher, for this totally flattering introduction. This immediately reminds me from the time 20 years ago. This was, of course, one of the reasons why I joined Christopher's group, because he's always so positive. Yeah, this is fantastic. And this really motivates you, and it's still the case. I appreciate this. It's really a pleasure to be in this big Hörsaal again after really more than 20 years, I think, when I last gave here some lectures myself. And it's great that you're all here for this adventure of the Birch-Swinnerton-Dyer conjecture. And I have to say, as a little disclaimer, there are some experts in the audience, and this will be boring for them. That's clear, because the lecture is really aimed to the rest of you. I want to explain a little bit what is it about, what is the topic of arithmetic geometry, and why the Birch-Swinnerton-Dyer conjecture is central somehow to many of developments and things we are doing. And so let me directly start here with introduction. And let's somehow pose the naive aim of number theory to be the following. So really the naive aim is you have some set of polynomials in variables, and say you have m of them, and let's suppose that these polynomials, the coefficients of them, they are all in Q. Yeah, so with Q coefficients. Then the naive aim would be somehow to describe all solutions of these polynomials with values in Q. Yeah, so describe solutions in so Q to the n, yeah, so tuples which satisfy these m equations. And of course, this aim is really much too naive because already for polynomials in one variable, it's very hard to find the roots, as everybody knows. Yeah? That's not an easy task. So that's too difficult. So what we can do, in Münster it's the other way around. I have to remember that. So we can do a much more modest aim here. Modest aim. And this would be just to say, do these polynomial equations have finitely many solutions or infinitely many solutions? This sounds really like a small step only, but already this turns out to be very difficult. Yeah? Or infinite. Okay, so now let's look a little bit. So if we have these polynomials, you can think of them as describing an algebraic manifold. Yeah, the zero sets of polynomials, this is like the zero sets of differentiable functions. So they describe a certain manifold, which could have singularities, but in any case, they give an algebraic manifold. And let me call this V. And we assume here in this talk, and this is really just for the experts, so all the rest doesn't need to listen, so that it's non-singular, say, it's not important. And say it's projective. We look at the projective closure of this somewhere. Okay, and then the question is somehow, if we just denote the solutions by V of Q, the Q solutions to this system of equations, so the question is this finite or is this infinite? Yeah? Now, what could we do to tackle such a question? And I mean, these are manifolds, so let's look a little bit at examples. And the first example, we look simply at the dimension. So let's look at the simplest case. Dimension is 0. Then essentially what we're dealing with is polynomials in one variable. So everybody knows this is the solution, even in the complex numbers, but also in the rational numbers, are finite. Yeah? So this case is settled. Okay, so let's go one step higher. Let's say the dimension is 1. Then what we can do is we can also look at the complex solution of these polynomials. And if these polynomials are good, this is a complex manifold. In fact, it's a Riemann surface here. So we have a Riemann surface, and let's simply look at the topological classification. How do Riemann surfaces look like? So the easiest case is the following. This is the Riemann sphere. Yeah? So this is C union 1 point at infinity. And this is the topological classification, say this is the genus is 0 here. Yeah? And then, as many mathematicians know, but otherwise I just tell you, there's a classification, a rough topological classification of Riemann surfaces just by the genus. And the next step is genus 1, sorry. Genus 1. Then we have genus 2. And adding more holes to it, you get very big genus here. That's a topological classification. And now let's have a look a little bit what one knows. Is this still in the range? Very good. So let's see what one knows. So let's look at the genus 0 case. So here, if this has points at all, so if this is non-empty, then one knows already, for example, by the Riemann-Roch, the famous Riemann-Roch theorem, that V is equal to the projective line. So this is the C-valued point of this. So the solutions in complex numbers, this is just this Riemann surface. And then one can write, so the solutions in Q, which you have here, this is the elements in Q plus this point at infinity. So there are infinitely many. Now, the next step would be genus 1. These things are called elliptic curves. And the elliptic curves, these are the objects of the Birch-Swinnerton-Dyer conjecture. So we treat them not here, we treat them in the next section. So let's go a little bit further. If the genus is bigger or equal to 2, then we have a very strong theorem due to Faltings, who also studied in Münster, and who proved that then the rational points, this is what arithmetic geometers call these set of solutions in Q, this is always finite. So you see there's something happening here. If the genus gets big, somehow the variety becomes complicated, and there are fewer rational points, so fewer solutions. Yeah? Here, projective space is very easy, and elliptic curves is very difficult. And this is also very difficult, but there are not many points to be expected. Okay, so what's true, or what is expected, I should say, in the case of higher dimensions? If the dimension is bigger than 2, then there are conjectures due to Lang and Bombieri. And I don't want to do this precisely. It's a conjecture anyhow, so it doesn't matter so much. But just to get an impression, so the idea is as follows. So there is an open dense, there should exist an open dense subset, open dense, such that the solution set here is finite. And the complement we expect are images of projective lines, the union of projective lines, and algebraic group varieties. Yeah, this is the algebraic analog of the Lie group. So I will explain you in the next section that elliptic curves are exactly such algebraic group varieties. In general, we expect somehow that only infinitely many solutions can appear if we have sub-manifolds coming from these algebraic group varieties or projective space. Yeah? So that's somehow the exceptional cases. Projective space is very easy to understand, and you see that we are now focused somehow on elliptic curves. That's the main problem which we have. Okay. So with this, we're ready to go to elliptic curves. So this is as follows. So E, we now call it E, because this is so traditional. So we do it. E is an elliptic curve. So this is called an elliptic curve if the genus of E is 1, and of course the dimension of E is also 1. And there's a small condition which is convenient also to make here. So this set is non-empty. Yeah? And now we ask, are there infinitely many solutions or just finitely many? To understand this problem, we first have to look a little bit on this elliptic curve, what they are. So if we look at the complex solution to these polynomials, and I will write down the polynomial in a second, then, now I made it wrong. So this is a torus. And on this torus, we have two paths. Gamma 1, gamma 2. I should take maybe colored chalks, but one can see it. So this is a torus like this, and because it has genus 1, one knows that there is a holomorphic, non-vanishing differential form here, and one can then write this elliptic curve as the complex number divided by a lattice. And here the omega 1, omega 2, they are given by the integrals of this holomorphic differential form over this path. So these are periods in the classical sense. Yeah? So this comes quite easily out of the theory of Riemann surfaces. So these Riemann surfaces of genus 1, they have a very easy structure. And in particular, you see immediately there are a group, because you have a group here, the complex numbers, with respect to addition, and you have a subgroup, which is a lattice. Yeah? So in this case, this is a complex B group. Yeah. Okay, so the usual picture one draws here is you do it here. So you write omega 2, omega 1. Yeah? This is a fundamental parallelogram spanned by this lattice. So this is the lattice you get by extending in the complex plane, this by integer multiples, and this also. Yeah? And you get the torus from this by identifying opposite sides. Yeah? So I can do this for you. With any sheet of paper, you can easily build a torus, except that my notes get a little bit screwed up. Yeah? So it's like this. So that's topologically a perfect torus. Yeah? Okay, so that is how it looks like. And now, in this case, much more is known. In fact, this is true for all Riemann surfaces. By Riemann-Roch, they are all algebraic varieties, the compact Riemann surfaces at least. And here, it's quite easy. So there's a very famous function, and this is the Weierstrass P function. And the Weierstrass P function, this is associated to this lattice here, which I call lambda. So a function on this elliptic curve is nothing but a function on C, which is invariant under two translations. So it is double periodic. Yeah? This is not just like what you have in theory of Fourier transform, where you have one periodic function. You have a double periodic function here. But you can write down by the usual average process, which you would do immediately as a mathematician, you can write down a series here, only that for compactness reasons there are no holomorphic functions. They would be all constant. But here you need to have meromorphic functions. So you have to allow poles. And I can write down the series easily for you. So this is lambda in the lattice, but not 0. And then you take z minus lambda square minus 1 over lambda square. And you sum over this. This is a double periodic function. Double periodic meromorphic function on this torus. Okay. Now, if you look up a little bit and you play around with derivatives of this, the function is on C, yeah. This is a double periodic function, and because it is double periodic, it descends to a meromorphic function. Thank you, I should be more precise here. Yeah, so descends to a function on this, yeah, a meromorphic function. Now, what you can do is you can look a little bit at the derivatives with respect to z of this function. And after playing around, you see that there's the following equation true. So there are complex numbers a, b, such that this differential equation holds for the Weierstrass P function. And this gives you, in fact, a map from this torus to the projective 2 space as follows. So you map Z to something like P prime, comma 1, plus a point at infinity. And then one can show that this elliptic curve becomes here a projective manifold and described by the polynomial equation so after that you see that we started here with a complex manifold and we ended up with something which is described in terms of polynomial equations. Yeah? Now to find Q rational points here makes only sense if A and B are themselves rational numbers. Yeah? Otherwise, you will not find them. And if we assume this, then finding out if E has finitely many or infinitely many solutions comes down to finding whether this equation has finitely many or infinitely many solutions in the rational numbers. Yeah, so this fits here to the board. So if A and B are themselves rational, then we get that EQ is just the following set. So you take x0, y0, 2 elements in Q, which simply satisfy this equation. And then there's also the point at infinity. So now you say, okay, this should not be such a difficult task to decide whether this is finite or not. But if you start playing with these equations, then you see it's very difficult. Yeah? It's a very, very difficult question. And there's an example. So this is not always finite. Yeah, so namely, if you look at the following equation, this is the solution to this polynomial. Everybody can check this now. And we will see in a second, I will not prove it, but it turns out that in this case, this is a point which generates infinitely many points here. And the reason for this is, so remember one aspect of elliptic curves which we haven't somehow really seen on the algebraic side, and I will not make this explicit here, or maybe I could. So it's a fact. The rational solutions inside the complex solutions, this is a subgroup. Yeah, it's a abelian subgroup. And the idea for this, I think I have time to do it. So let's look at the real picture of an elliptic curve. So these are the real solutions. Yeah, I'm not able to draw the complex picture, unfortunately. So I want to explain to you how the structure the group structure could be algebraic. And the point is as follows. If I take 2 points here, which lie there, then the group structure, in fact, is as follows. So you draw the line through these points. Then you get an intersection point. Because it's a cubic equation, one knows that any line has to intersect this in 3 points. Yeah? So you get a third point, but this is not the addition. So there is 1 point up there at infinity, and you draw a line through infinity and this point. This looks like this. Yeah? And then you get a point which we call P1 plus P2. And it turns out that this is really exactly the algebraic description of the group law which we have there, which gives this complex Lie group structure. Yeah? That's already very surprising. Yeah? And because this is just intersecting of lines with cubic equations, you can imagine that this is a completely algebraic process. You can write down polynomials in the entries to give this point, and this is an algebraic equation. So this gives an algebraic group structure. Okay, but there's more to it. There's a famous theorem by Mordell and Weil, and Christopher told me he just talked about this in his lecture today, so I hope some students are here also. I don't know. They don't like adventures in mathematics, maybe. Okay. So, and this says, and that's really surprising if you see it for the first time. So the set of solutions, this is a finally generated abelian group. And what does that mean? This means simply, you can write it as follows. So EQ, so there are some copies of the integers, say R copies, and then there's a finite abelian group. Yeah? This is a very, very strong and deep theorem. Yeah? It uses very sophisticated estimates of points on the projective space. This is called the theory of heights, and this is really a deep theorem combination of many different ingredients. Okay, so now let's back up a little and see what we have achieved here for our problems. What we want to study is are there finally many solutions? Does this contain finally many points or infinitely many? Mordell-Weil says, oh, this depends on this. This depends, R is 0 or not. Yeah? So in particular, EQ is finite if and only if this R is 0. Yeah? So now we need some tool to decide whether R is 0 or not. And now you think, okay, this is an algebraic problem, etc. So there should be a rule given this polynomial equation, yeah, to you with coefficients, and then you say, yes, infinitely many points, yes, finally many points. But nobody has found such a thing yet. Yeah? And if you look at these equations, yeah, for example, there are very similar equations like this, where you have only finally many points. Yeah? And the solution which I have written down here, so in this case, yeah, so in the example case, now I have to erase something, but let me explain this first. So in this example case, the R is 1. Yeah, one can prove this. This is already not easy. The R is 1, and the point which I have written down is exactly a generator of this. Yeah? That's what's happening here. Okay, so now the big question is, how could we possibly solve this riddle? So, now, the solution of this riddle, it's not really a solution because it will come down to a conjecture, but now really a totally different idea is needed somehow to understand what's going on. And you have to introduce the L function. So let's assume now that A and B are really integers. Yeah? One could clear denominators, then you get a slightly different equation, but let's simply assume A and B are integers. Then it's very classical what you do, and I think everybody knows, if you cannot solve such an equation, you might look first somehow if there are solutions when you just calculate modulo some number. Yeah? So let me make this precise. So look at, say, points x0, y0, pairs of integers, such that you don't have an equation right on the nose, but you have solution to such an equation, modulo p, where p is a prime number. Yeah, this means we consider two numbers to be equal if the difference is divisible by p. Yeah? And you can do this. This is, of course, a much weaker problem. And this amounts to, this is the same as looking at solutions of this equation in the finite field Fp with p elements. Yeah? So we denote this by EFP. Now, this is a finite field which has exactly p elements, and this means there can be only finitely many solutions. Yeah? You have only p squared possibilities to put in for x and y, so there are only finitely many solutions. That's clear. Because our group law was algebraic, this is even a group. Yeah? So this is a finite abelian group. We are only interested in the fact that it is finite, but I just want to point that out. So somehow we look at this easier problem. And what the people in arithmetic geometry like is to look at the following arithmetic picture. This is somehow the geometric part of arithmetic geometry. So we sketch here, this is a picture of Z, but somehow, for some reasons, we look only at the prime numbers in there. Yeah? And now, we think of this elliptic curve, of this equation, which is defined here for integers, as a family of elliptic curves. This is not a single object, so it's a family. So over each prime, there is such an elliptic curve, which is an algebraic variety over that finite field. Yeah, so, etc. Yeah, they form a family. This is the arithmetic geometric picture, I should say, but I think that's. So over each fiber, over each prime, you have such a curve. And somehow this equation looks at them all together. Yeah? So, of course, if you now look only at these solutions, they know, I mean, because there are only finitely many, they cannot know anything really, it seems, about the possibility whether this is finite or not. Yeah? Because if you have here infinitely solutions, if you look modulo p, you still have only finitely many. Yeah? So what have we gained? Nothing. Yeah. That was really in vain. But let's see how that works. So, but now, let's make a very, very simple invariant for this elliptic curve. So we define an integer for each prime number p. We take p plus 1 minus the number of solutions over in this finite field. So minus the number of solutions modulo p of this equation. Yeah? So this is a finite number. That's no problem. So there's no problem to define this. Okay. So, and then you define the L function as follows. The L function of E, this depends on a complex parameter C, and this is defined to be an infinite product P, and for some reason, yeah, maybe I write it, so P should not divide the discriminant of this equation, but you can forget it. This throws out finally many P. So, and then I do the infinite product as follows. So I take AP times P to the minus S plus P to the 1 minus 2S. Yeah, S. And it turns out by an old theorem of Hasse, which gives a rough estimate for this, which is in fact not so rough, it's really good, this converges. Converges if the real part of this complex number is bigger than 3/2. So this is now, so what have we done here? We took this number of solutions in this finite field, which are finite, and we make a function which somehow encodes all these, finally, the knowledge of these, how many points are there over this finite field. Yeah, and of course, if taking logarithmic derivatives, etc., you can recover this also from this. It's a little bit difficult, but in principle, the only information which is there is something which is an information somehow in each fiber, but nothing global. Yeah, this is a kind of local information. Okay. So, and now the results by Andrew Wiles on the Shimura-Tanyama conjecture, this implies that this function has an analytic continuation to the whole complex plane. Yeah? Okay. And now, after all this, we are prepared to understand the Birch-Swinnerton-Dyer conjecture. So, and that's just the following conjecture. So if E is over Q is an elliptic curve, so this means this equation has coefficients in Q. So AB is in Q. Yeah. So that EQ is this finally generated abelian group, R plus some finite group. So we want to know about the R. And here's the conjecture. So R is just the vanishing order at s equals 1 of this L function. That's totally surprising. Yeah? So, in a certain sense, if you accumulate all the knowledge of the solutions over finite fields, yeah, and you put this into this generating series, if you like, then they know. This series knows whether you have an R, positive or negative here. Yeah? So in particular, it says, so in particular, so R is 0, so EQ is finite. If and only if this L function does not vanish at 1. Yeah? Strange, right? It's really strange. How could one ever cook up such a conjecture? Yeah, so that's really, I mean, I have to say that there are some analogs over number fields. The time is not sufficient to explain this. And then, really, Birch and Swinnerton-Dyer calculated these things, these solutions, for hundreds of elliptic curves. Yeah? And back then, in the 60s, when this conjecture was conceived, it was very hard to buy the computing power at the big machines. Yeah? So that was really a task. And if you read some of the recollections by Birch about this is very interesting to read. Yeah. So that's a conjecture. So there is somehow, it seems, no direct way to look just at the equation and the coefficients and then to say, okay, with this coefficients, the elliptic curve has to have infinite many solutions, but you have to compute somehow this L function. Yeah, that's the point here. So maybe I say here, 5 minutes. So there is even a refined version which is interesting because although I cannot explain this too much, I just write a complicated formula now. So so this has vanishing order R, so we can look at the first Taylor coefficient, which is non-zero in the Taylor series development of this holomorphic function. Yeah, this we can do. I write it as follows. So this is just s minus 1 to the r. So this is the first Taylor series. And the interesting thing, it's conjectured that almost all important arithmetic invariants of this elliptic curve appear there. Yeah, so the formula is as follows. So these are the periods of the elliptic curve. Then there is the famous Tate-Safarevich group here, which is not known to be finite, but is conjectured to be finite. Then you have to take the order here. There is the determinant of the height pairing of the points of the infinitely many points. There's a 2-factor. And then there is, this is written like an infinite product, but it's in fact a finite product. This has to do with bad reduction of the curve, where it's no longer an elliptic curve, and you divide the whole thing by the number, the cardinality of the torsion of this group. So this is this finite group, which appears here, the cardinality of this to the square. Yeah? That's absolutely amazing that you expect such a thing. Yeah? And Now, maybe in the last 2 minutes, let me just mention what is known. Because in fact, by now, there is really a lot of things known. I mean, you would never think that you can prove such a conjecture. Yeah, I mean, how to do it, really. Yeah? And the techniques use very much the theorems of Weil's, which says that this L function which you have here, this is an L function of a modular form of weight 2. Yeah, so modular form is a function which satisfies even higher symmetries than just being double periodic, which are very, very important in number theory. And with this help, you have the theory of modular forms available, and this is a huge subject in number theory, yeah, and many, if not all, results concerning the Birch-Swinnerton-Dyer conjecture are related to this. So there is work of many people, and let me just give a little upshot. So the most important work maybe, so I cannot mention everybody, yeah, I say this because there are too many. I forget important contributions here. I'm sorry for this, yeah. But the one of the most important work is really the one of Gross, Benedict Gross, and Don Zagier in the 80s. And they proved essentially the following. So if the order of vanishing is 1, then the rank, so this R, which appears there, this is bigger or equal to 1. And then came Kolyvagin, slightly later, 88, and he could prove with refined methods that, first of all, if this doesn't vanish, then the R is really 0, and this Teichov-Arevich group is also finite. At least the P part for many P's, almost all. P. And if you combine this, then this gives you that whenever the order of vanishing is less or equal 1, then you know that R is exactly the order of vanishing. S equals 1 of this L function. And now, what is maybe very interesting, so there is a lot of work done by Skinner, Chris Skinner, Eric Aubin, and then Yetchev, Skinner, and Van, and many more. And they prove that in this case, yeah, so if the order of this is less or equal to 1, then in a certain sense, the P part of this formula, of this refined version, is true for almost all P. It's true for almost all P. Yeah? I think I stop here. Thank you very much.
Die 7 größten Abenteuer der Mathematik.